Okay, we again record the lecture and I switch to English. Let me pick off where I left you, which was the calculation of the beam luminosity. This pertains to both E plus E minus colliders and hadron colliders. What we're doing now is we calculate from first principles, because it doesn't take long, the luminosity that comes from colliding two bunches. I will now share, as usual, my drawing board. This should happen now. Maybe I have to unshare here. Okay, you can see it now. And I made a sketch of the situation. We have two bunches that collide with each other. This complements and this completes the calculation, the discussion we had in the last lecture. Good. So first, let's make sure we understand what the units are. The number of events in a collision is typically given by luminosity times cross-section. The luminosity has units meter to the power of -2, and the cross-section, you can think of it as a geometric cross-section, is comes in a square meter, or more conventionally inverse square centimeters for the luminosity, and for example, nanobarn, femtobarn, picobarn for the cross-section. So that's just to understand what we are talking about in terms of units. Now, let me write down what the luminosity is for a bunch crossing of a single bunch. So we have a four-dimensional integral. We view these bunches as we think of these bunches as they go through each other versus time. So collision happen at each time with a certain rate that's proportional to the cross section, and the spatial and time integral, it's of course proportional to the two densities of the bunches. We call them rho 1 and rho 2, and to the relative velocity of the two bunches. Since the colliders, operate at energies way above the rest mass of the particles, we are in the ultra-relativistic regime, and this relative velocity in the lab frame, so we do our calculation in the lab frame, is 2 times the speed of light. We now change variables. I call the variable z in the direction of the beam s, and we call the variable, we change the variable of time to s0, we just call s0 c times t. So let's rewrite this integral. Ex, dy, ds, ds0 four-dimensional integral times rho 1, and we assume the density depends on the spatial coordinates x, y, z, and s0, and the second bunch is I'm sorry, there's a mistake. Minus S0. Now, that's in principle everything. The factor C got, there's a factor 2 here. The factor C got, of the speed of light got absorbed in the redefinition of the variable we integrate over, and that's it. Now, we make now simplifying assumptions so that we can perform these integrals. We say that the densities of the two bunches we write as S plus minus S plus minus S0. And we say there are Ni particles in each bunch, and they have Gaussian width. So the distribution of the particles inside the bunches follow normal distributions in all three spatial directions. So this is easy to write. First of all, we separate the dependence on the coordinates. S plus minus is 0. So here we have our colliding bunches in for the two directions along colliding along the beam direction. And then we say for x, y, and s that our, I write it down for x, that the profile looks like this. It's a normal distribution, which is given by 1 over square root of 2 pi times the width of this distribution times e to the minus x squared divided by 2 sigma x squared. So this is just the probability density function of a Gaussian or a normal distribution. We will use that the integral of this distribution is 1, which is easy to check. Yeah, this is a normal distribution. Good. So let's insert now, because everything is completely straightforward. From now on, the luminosity for a single bunch crossing is therefore given by our four-dimensional integral, then the factor of 2 from the relative velocity, and then I have a product of the two densities. So I write the two particle numbers n1 and n2, and if we count the numbers of square root of pi, there's a total of 6 of them, because each density has 3 Gaussians in it. And then we have simply from the normalization here, sigma x squared, sigma y squared, and sigma c squared. And then this needs to be multiplied with an exponential, and the exponential is minus x squared over sigma x squared minus y squared over sigma y squared minus, and here we have s minus s0, that's the moving bunches, plus s plus s0 squared, and here it is 2 sigma c squared. Remember, there is a factor of 2 in the denominator in the exponent of the normal distribution, because I have assumed that both bunches have the same width in the x and the y direction. There is a factor of 2 here that cancels this. So we have to compute this integral now. We use the following small trick. We know that the integral, the normalization integral of the Gaussian is, write it down here again. This quantity is 1, and therefore we know that it follows that the integral of e to the minus x squared over sigma x squared, which is one of the integrals that we need, is square root of 2 pi. And then if you absorb this factor of 2 here in the sigma x, you will find that this is 1 over square root of 2 sigma x. So this is just square root of pi times sigma x. And we are ready to put everything together. So the single bunch luminosity is 2 times n1 times n2. Let me move it. Divided by 2 pi cubed, sigma x squared, sigma y squared, sigma c squared, and square root of pi sigma x, square root of pi sigma y, and here we have from these two integrals we get square root of pi sigma c squared. So canceling the square root of pi's and the sigmas, we note that nothing depends on the width of the bunch in the z direction. This is because if it's longer, then it will just collide for a longer time, and we will get the same amount of collisions. But it is important that the bunch is collimated in the x and the y direction, because the single bunch luminosity comes out as a factor of 2 cancels, comes out as n1 over n2 divided by 4 pi sigma x times sigma y. So it's proportional to the product of the particles in the two bunches, and it increases with 1 over the width for both the x and the y directions. Hence, we want to focus our beams very very tightly and have large densities, large numbers of particles per bunch, and have them collide. It's less important how long these bunches are. Let's take some typical values. At the LHC, sigma x and sigma y at the design is 16.7 microns. In 1 and in 2, the number of protons is very roughly, I took this from the design specifications, is 115 billion protons per bunch, with 115 billion protons in a single bunch. And then we have, what we haven't used so far, we have 2,808 bunches at the same time in each of the two counterclockwise rotating beams in a counterclockwise fashion. And the revolution frequency of a single bunch, because the circumference is 27 kilometers, and the speed of light, it follows that the revolution frequency is very roughly 11 kilohertz. So a single bunch comes back with a frequency of 11 kilohertz at the specific interaction point. We can therefore calculate the beam luminosity as the number of bunches times the frequency times the single bunch luminosity we've just calculated, we find, let me write it down, that this is the number of bunches times frequency times the population of the bunches divided by 4 pi sigma x times sigma y. And if you put in the numbers, you will find that this is 1.16 times 10 to the 34 centimeter inverse squared per second. We now change to the units that we use in high energy physics. So 10 to the 34 inverse centimeter squared. That's the instantaneous luminosity, so the luminosity at a given time at the LHC for the design specification on average. We change the units. Let's see what a nanobarn is. A nanobarn is, of course, 10 to the minus 9 barn. What was a barn again? A barn was 100 square Fermi. So we have 10 to the minus 33 centimeters squared. That means the LHC beam luminosity is very roughly 11.6 inverse nanobarn per second. This is the rate we accumulate data with. This rate has to be multiplied with the physical cross-section of a given process to arrive at the event rate of that process. So if you want to know how many Higgs bosons per second we have, you need to look up the production cross-section of the Higgs boson and multiply it with this number, and you'll get a rate. You also have to, if you want to know the total number of a certain particle species that we have, you have to know the availability of the machine over the different data taking years, which just means you need the time integral of the instantaneous beam luminosity that we just calculated. And let me give you the number. For the LHC run 2, that was from 2016 to 2018, we have very roughly 150 inverse femtobarn of luminosity. So if you multiply this integrated luminosity with your favorite production cross-section, you will arrive at a number of events for the process, and then you can start analyzing the data and try to understand what has happened. Good. So this completes our cross-section calculation. I advise you, as usual, to follow these steps. I stop sharing. I share back the slides, and we very briefly recap what we discussed last time. Here we are. The full calculation is on the slides as well. I don't think you need, I don't even think you need the recording, but it might be helpful in case you get stuck at some point. So we calculated very roughly LHC design luminosity of 10 to the 34. Let's keep this number in mind because we will discuss because it will come up in the discussion of the European strategy and competing collider projects, because obviously the rate we take data with is something that's critical for the physics performance. Good. I hope you can see the slides. If you don't, please screen. let's look again at the typical cross sections at the LHC. The total cross section of proton-proton collisions is 80 millibar, and it's up here. Typical cross sections of interesting processes are in the nanobahn and the femtobahn regime down here, which means, which is just to say these numbers are much smaller. In other words, we typically have 1 billion or so of uninteresting collisions before something happens that we really want to record and to study. Let's look at some numbers. The LHC rates for 13 TeV for the production of a TT-bar pair. So that's a pair of 2 top quarks. You can extract from this red line here at 13 TeV is very roughly 1 per second. So we record 1 top quark per second, and over 3 years or so we get tens of millions of top quark pairs that we can analyze. The Z boson is an important particle because we understand a lot. It has been studied extensively at the E+ E- lab collider. We produce it with roughly, it is this line here, the green one, with 2 orders of magnitude more, so 100 hertz. We record roughly 100 Z bosons per second. The CMS detector can record with roughly 800 hertz. So the 100 Z bosons are a good fraction of the total amount of data that we are taking. Let's look at E+ E- colliders, because see, these are hadron-hadron, proton-proton machines with very large production cross sections of roughly 80 millibar. If we look at the lab collider, this is the top plot shows the cross section of E+ E- collisions as a function of the collision, as a function of square root s, the collision energy. This is for the numbers I give here are for lab operated at the Z pole. So we adjust these are, it's in a + E- machine. The beam energy is adjusted to the resonance, to the Z resonance, and the cross section there is only 60 nanobar, and there is a branching ratio of 3.4% to muons, which gives us 2 nanobar. The instantaneous luminosity, so the luminosity per unit of time at lab was roughly in the order of 10 to the 32, so 2 orders of magnitude less, which means roughly 0.1 nanobar per second, and every 5 seconds a Z boson. Now we have, as we said before, at the hadron at the LHC we record Z bosons with 200 hertz. That is a whole different game. So that's why we say a hadron machine is a discovery machine. Everything happens at the same time with very large rates, unfortunately also in a very large background. Most of the events are not interesting. It's just quarks scattering with each other, at each other, and nothing interesting happens. But nevertheless, if you compare the cross sections here, typical numbers are much larger, and if you manage to record the data, you can do typically more physics at the hadron collider, because all these processes happen at the same time. At E+ E- colliders, you do have to adjust the beam energy. So you're operating the collider at each at a certain beam energy. That's not different to a hadron machine, but in the hadron machine, protons collide, and protons consist of quarks. and the quarks carry a varying fraction of the momentum in each collision. And hence you're spanning orders of magnitude of collision energies with respect to the initial particles. While if you think of any plus and minus machine, it's really the particles that you accelerate that are the initial state particles of the collision of the process in question, and hence you need to adjust the beam energy to where you want to look. In other words, if you want to measure the shape of that resonant peak here, I hope you can see my mouse cursor. Then you have to change the beam energy each time, and that costs time. On the other hand, once you do that, and if you move further out here towards higher energies until you're limited by synchrotron radiation, the events are much cleaner, because really only you will really you do not have you do not have these garbage bags of protons with their many constituent particles colliding, but just the E plus and the positron and the electron that you accelerated. I put here below a plot from a plot that extends what we know what happens if you move further out in energy. You see all sorts of interesting processes popping up. So that's the C boson, one of the standard model particles. We're going to discuss that in a few minutes. If you move further out, things become very interesting. You produce two Ws, a Z boson and two photons, two C bosons, and other processes that are worthwhile to study. Good. So this completes the discussion of the luminosity. Let's look a little bit of what are the difficulties in operating colliders. Emittance and amplitude function. We had in our single bunch luminosity, we had sigma x and sigma y in the denominator. So these are the numbers, the widths of the beams that have to be small. In collider physics, these are rewritten as a product of the emittance and the amplitude function. This is not something I'm going to ask you, of course, at the exam, but it is worthwhile to explain it once, because these are typical concepts that are used when these are the typical concepts that collider discuss the quality of the machine. So the transverse emittance has a length of has a unit of meter, is the smallest opening angle the particle can fit through. So it is, in principle, it gives you the scale of the width of the two beams at the interaction point. We think of it, so we are here, and here the two beams cross. The amplitude function is beta star, and it defines the distance along which this amplitude, this diameter doubles. The simple geometrical expression is given here. What I want to say is that there's a Liouville's theorem. The Liouville theorem pertains to the phase space of the protons in the bunches, because they have different momenta, and in X and Y, and also in C, they have different positions. So if you think of the six-dimensional phase space of the three momenta and the three locations, the particles in the bunch will occupy a certain phase space volume. Liouville's theorem tells you that for the interactions that you can control, the electric and the magnetic ones with the dipole magnets and the focusing, in particular with the focusing magnets, the phase space volume stays constant. And you can see this here in this sketch. We can focus the beam a little bit stronger, make beta star small, but then once we do that, the beam blows up further and more quickly after the interaction has happened. That means Liouville's theorem is a limit to how well we can optimize the instantaneous luminosity. It's basically just saying that if you focus perfectly fine in, if you focus perfectly in the radial direction, the x and the y direction, for example, then you get a large spread in the momenta of these particles, and it becomes more difficult to control the beam particles afterwards. And hence, there is only a limit to where we can get with each specific collider. We cannot increase the instantaneous luminosity indefinitely by focusing, for example, just by focusing. Good. The emittance, so that is the role of the amplitude function. The emittance is the smallest opening the particles can fit through, and is in principle completely determined, also in a very complicated way, by the quality of the injection chain and the bunch preparation. So this already starts with the linear accelerator at the beginning. The bunches have to occupy the smallest possible phase space volume, have to be very close together in a spatial direction, and they have to have at the same time very similar momentum. Then the emittance is low and our instantaneous luminosity is high because it appears in the denominator of the formula for the instantaneous luminosity. Typical sources for emittance blow up, which means well, bad emittance and low instantaneous luminosity, are, for example, mismatches at the injection between the accelerator stages, for example, from the SPS to the LHC. Scattering on beam gas particles. Unfortunately, the vacuum in the beam pipe, I mean, it's 27 kilometers long, the two beam pipes. The vacuum is very good, but it's not perfect, and scattering on beam gas particle blows up the beams a little bit. And then you have resonances of the beams with the mirror currents, with the electron cloud, and with electromagnetic fields in cavities and other instabilities. So this is really it's a field of science in its own, and has to be developed during the second half of the 20th century, where we really understood how to operate these machines and to achieve good instantaneous luminosities. Typical values for beta star at the LHC are 15 to 50 centimeters. So that's very roughly the size of the spread along the z direction until the smallest diameter the beams fit through move out to twice that value. Good. A few problems that people face when colliding proton beams. Wake fields, in German Kielwelle. Think of a charged particle moving with ultra-relativistic speed. You know that the field lines are collimated perpendicular to the direction of the movement. That's depicted here with this sketch. The longitudinal extension is very roughly, I mean, it's actually, to good accuracy, is proportional to 1 over gamma. So can be very narrow for these highly relativistic particles. And then a bunch of particle moves, let's say, through the beam, and then let's say there is a cavity, for example, for a vacuum pump. Okay, so you look at the cavity on a computer, you design it, and you do Fourier transform in the z direction, for example, and one then sees from these sharp edges, one sees resonance structures in the Fourier decomposition. So that means the impedance in electrodynamic terms, the impedance is highly dependent, highly non-trivial, and highly dependent on the frequency. And what's happening is this: see, there is a single bunch here. The time goes from bottom to top, and the beam direction is from left to right. So here's the bunch of particles, and the electromagnetic field that it causes is colored. And then it passes through this cavity, if we follow this track, and it leaves again, and it leaves behind from these resonances in these cavities an oscillating electromagnetic waves that then perturb the following bunch, because remember, the bunch spacing of the proton bunches in the LHC is roughly 70 centimeters. So this is to show that each component of the beam pipe has to be designed very carefully, because it's Fourier transform directly, if it's peaked, if it has resonances, causes strongly oscillating waves, because these resonances are then excited, and the next bunch hits into such an electromagnetic wave, and that would lead to a blow up of the emittance and a reduction of the luminosity, because there is then more spread in the phase space of the particles in the beam. Another problem are electron clouds. The left plot here is a computer simulation. The computer simulation puts electrons in the radial direction. So these blue lines are electrons, and you have a bunched beam going into these simulated electrons from left to right. So you see that the trajectories of the electrons are bent. Because they are negatively charged and the proton is positively charged, and they are bent, they are accelerated, and they hit the wall, they hit the beam pipe, and their density there, the density there is increased. So this means stray electrons in the beam pipe, if a bunch goes through, are accelerated in the radial direction and hit the beam pipe with large enough energy that they can, in principle, release more electrons. And if you have more electrons, the next bunch can then do the same and increase the amount of electrons further. So what you can get is oscillating electron clouds between the walls of the beam pipe, resonantly driven by the proton beam. And this at the end can release debris that may be stuck to the beam pipe somewhere, and can also interact itself, so the electrons can interact with the beam. And this would also reduce the emittance of the beam. It would make it causes resonances that are difficult to control, and would ultimately reduce the achievable luminosity. If a large particle is if a larger, like a dust particle, is released somewhere from the beam pipe and hits the beam, then you get, remember we looked at this battleship, the kinetic energy of the particles in the beam is intense, is very high. We talk about we talk about hundreds of megajoule. So we have a megajoule hitting a dust particle. This causes an intense radiation, burst of radiation that will hit the superconducting magnets, the dipole magnet, and it can cause a quench in this magnet. So it can make parts of this magnet normal conducting just by means of radiation, in which case the beam has to be dumped and the magnets have to be ramped down. That's very dangerous for the operation of the LHC, because if you have such an occurrence every half hour, you can never operate the machine. Fortunately, there are ways to mitigate it. One can inject very large bunches at low energy and drive this electron cloud on purpose until and the low energy then causes less dramatic beam interactions, and in this way remove the debris from the beam pipe. These are called scrubbing runs. So it's just wieder Rauchfangkehrer. We have to use high intensity bunches to scrub the whole beam pipe so that we can operate the collider safely. By the way, it was not known when we started up the LHC 10 years ago what the rate would be, because it has not been tried. There were single events with very large losses, which we thought were coming from unidentified falling objects in the beam pipe. So this would be the dust particles, or UFO in short. So when we talk about UFOs at the LHC, we mean dust particles falling into the beam and causing quenches in the magnets. A few more words on the operation, that you get a feeling what has to be achieved. The top right plot shows the LHC beam profile. I put the scales here. Pay attention to the scales. On the X and Y directions, it's 5 millimeters. So here we have our 16.7 diameter, 16.7 micron single bunch width. And they are collimated and brought to collision at the interaction point, but this distance along the Z direction is plus minus 50 meter. So this 50 meter, these interactions with the focusing magnets that are shown here, they happen outside the experimental hall. So this whole picture is really, in reality, it's stretched by very large factors. You have the detector in the middle, and then 50 meters away with a 5 millimeter distance, is the last time where you interact with the beam, and then they are on their ballistic trajectory and brought to collision at the center of the experiment. Now, if we want to measure, if we want to do physics measurements, we have to know how many events we expect, because ultimately we want to compare theory and experiment. The theory gives us a cross section. The experimental facility must tell us how much luminosity it has achieved, so that we can compare the predicted number of events with the observed one. Now, it's not easy to measure the luminosity because you cannot just put the monitor inside the beam pipe. You have to do this with for example, with the decay products of the primary collisions in detectors that are far away from the interaction point, that measure on average what the luminosity was. These are these are called a Brand detectors, where N stands for neutrals. So this measures the neutral particles from the many collisions that happen simultaneously. One key tool to measure the luminosity are Van der Meer scans. A van der Meer scan is a displacement of one beam with respect to each other. So one holds one beam fixed, and then one moves the second beam and displaces it transversely. What one then finds are reduced values of the integrated. One finds reduced values of the luminosity, and from this one can infer the beam profile, whether it's Gaussian, what its width is, in both directions, and from that one can infer the instantaneous luminosity. So when we operate the beams, usually the beginning of the year, the beam optics is specified. After the machine is set, we perform for a few hours at least, a few days, van der Meer scans where we displace the beams and monitor the event rates to get a good idea about the instantaneous luminosity that we're going to take. Some emittance blow-up is unavoidable. It means there will always be a rate of interactions with beam gas, some misalignment in the injection system, and there are also the collisions happening at the detector. All this leads to bunches that blow up, for example, in the longitudinal direction, so that luminosity drops and the beam is less under control. That needs to be stabilized. One way to stabilize the beam is stochastic cooling. Imagine, for example, a bunch hits a dipole magnet not exactly perfectly. That means it will be kicked back on its trajectory, and then it will hit for example, the next dipole magnet even stronger. You can pick up transversely oscillating modes of the bunches as they go around the beam. That's dangerous because if there is an energy source that's driving it, for example, electron clouds, at the end of the day, it can mean that you lose the whole beam, because it's very hard. What I'm trying to say is that it's very hard to control the oscillation of the bunches in the direction transverse to the beam. What one can do is pick up a signal of this movement at one side of the ring, and because the particles move with the speed of light, they have to. You can overtake them by sending a signal with the speed of light across the ring and drive a kicker magnet, for example, or a kicker electromagnetic field that removes this oscillation again. So imagine so a bunch oscillates. Wait, how would this go? A bunch oscillates, hits a pickup, goes through a pickup cavity where measurement of its position is performed, and then a signal is sent across the ring. I mean, the diameter is 27 kilometers, and then a kicker magnet is precisely adjusted to compensate for this oscillation, and then I hope you can see the mouse cursor, and then this movement is cooled and the bunch follows the ideal orbit. That's an invention also by Simon van der Meer. He invented both of these things on the slides, and both of these, I mean, the van der Meer scans for the luminosity measurement and the stochastic cooling for operating the beam in the presence of disturbances is something that makes operating colliders possible. Both of these are really necessary and everyday criteria, everyday things, everyday procedures that are carried out at operating these colliders. So I talked about a lot about the LHC. Let's look at the E plus E minus collider, Super KK. This is a collider that operates at the epsilon 4s resonance. It collides 7 GeV electrons with 4 GeV positrons at an energy at the energy of the 4s epsilon resonance, because that one decays to BB bar pairs, and those are the interesting object. Those are the objects that are interesting that are most convenient for studying B physics. This E plus E minus collider currently leads the luminosity record. It has achieved 2 × 10 to the 34 centimeters squared, 2.22 × 10 to the 34 inverse centimeters squared per second. That's slightly higher as we could achieve at the LHC. However, the target is 8 × 10 to the 35 when it is fully operational. The world record was only set this year in June, so they are now they just overtook LHC in terms of luminosity, hence we call this the luminosity frontier. It was achieved by a so-called nanobeam scheme. They have their beam width of nanometer sized, and it was possible with a peculiar configuration of magnets and beam optics to reduce the size of the typical size of the beam from 220 nanometer to 50 nanometer. And I put a picture of the beam profile that put a picture here to give you an idea about the beam profile at Super KKB. This is the overview of the KKB facility. It's not as high energy, hence the magnets are not that limiting, and therefore it need not be completely circular. You can tolerate a bit stronger bending radii here. Here's the Bell 2 detector. We'll talk about a lot. We'll talk about the Bell 2 detector a lot in the upcoming lectures. So Super KKB is leading in luminosity. LHC is leading in terms of energy. Let's look at the history from the 70s to 2020. And the peak luminosity in inverse centimeters squared per second on the y-axis, you have you see that we roughly could achieve, from technology perspective, a roughly exponential growth. The y-axis is exponential. I'm sorry. The y-axis is logarithmic. The x-axis is the time is linear, and you see very roughly that we could achieve Moore's law, a doubling of the peak instantaneous luminosity versus a constant time interval. Here's the SPS pre-accelerator for the LHC. Here is LAB. Here is LAB 2. LAB 2 goes up to 10 to the 32, as we said. LHC is here, 10 to the 34, 2 orders of magnitude higher, and uses protons. The world record, Super KKB, we just discussed, is here, 2.22 times 10 to the 34, going up to 10 to the 35, many times, then 8 times 10 to the 35. This is absolutely the luminosity frontier, highest collision rates, worldwide. However, as you know, E plus, E minus cross sections are much lower. And the upgrade of the LHC, the high luminosity LHC colliding protons, will go up to 10 to the 35. The operation will start in 2026, and here this is corona corrected, is very likely to start a year later, 2027 to 2037, and that's as far as our current experimental planning horizon goes. So we plan 15 years or so in the future with the facility that we have. Speaking about facilities, let me give you a brief overview what facilities existed in the past and exist now. I don't think I should read out the list. It's worthwhile to look at it and Google the ones that you don't know. SLC at SLAC in Stanford was a discovery machine. DESI, electron-proton collider for deep inelastic scattering with the Zeus and H1 experiment, are very important to measure. We're going to talk about it today, to measure the quark and gluon content of the proton in deep inelastic scattering. Then we've discussed the lab collider at CERN, E plus E minus machine, operating with beam energies up to 104.5 GeV, limited by synchrotron radiation. It was our example, and luminosities of 10 to the 32. Then there are smaller machines, Novosibirsk Web. Then in China has a BEPC2 collider with the BES3 detector that is operating now and studying, for example, studying rare hadron decays. Then the SPS has been in operation until the 90s, was the proton and proton antiproton machine had the UA1 and UA2 experiment, which discovered the W and the Z bosons. And then we have CERN again, then we have LHC at CERN, operating now currently at 13 TeV, collision energy of 13 TeV square root S, beam energy 6.5 TeV, and instantaneous luminosity of 2 times 10 to the 34. So probably the numbers in these lines is something that you should know for the LHC and super K, KB. The other numbers are something, the table is here for reference and to look it up. Let's look at the Livingston diagram. This is now back to the energy frontier, which is discussed, the luminosity frontier. This is the constituent center of mass energy versus time. Again, we see exponential growth, Moore's law, doubling of the energy every constant period. This is a very old plot. It only, it's a pre-LHC plot. It's more than 10 years old. But you can see that we could achieve doubling of the energy for over a constant period for the second half of the 20th century. And very important for this was where the technological advancements. For example, what we've discussed, stochastic cooling really was necessary to control the oscillations of the beams, as I tried to explain you. Superconducting cables at the tevatron, superfluid cryogenics. The LHC dipole moments are cooled with super fluid helium. It wouldn't otherwise be possible. And this led to the discovery of the Higgs boson. So enabling concepts of collider operations allow us to push higher towards the energy frontier. The present and the near-time facilities are the LHC with its upgrade, the High Lumia LHC in 2027. Super KKB just began in Japan for E+, E-. Now let's talk about a little bit about the future further down the road. I want to tell you, because it's being discussed in the media, and if you follow the Twitter feeds of physicists in Europe and the US and elsewhere, you'll see discussions about the European strategy for particle physics. Let me tell you a few words about it so that you know in what situation the whole field is now. Of course, this is also not something I'll ask you at the lecture, but I want to educate you a little bit about how the community views the fields and what the discussions are also pertaining to politics. So as you've seen, these colliders, they're big, expensive, and only achievable because the whole community puts together the funding in one box and funds large projects. That has worked nicely in the 20th century, and we try to carry that over into the 21st century. So to see where we could be going, the CERN Council set up the European Strategy Group to define a future strategy. So that one needs to discuss the technological challenge of building larger colliders to meet the big physics questions that we have. What's the origin of electroweak symmetry breaking, for example? And then we must respect the limiting collider, the limiting factors for the colliders that we've discussed, which is synchrotron radiation and the magnetic field in the magnets for the hadron machines, which do not suffer from synchrotron radiation. So people at the highest level of politics and at CERN management discuss these questions in the same terms as we are doing, comparing synchrotron radiation losses and comparing luminosities, comparing magnet strength, and at what time scales we think that future magnets might be available. The important areas of future research, that's a little bit my opinion, although I took it from the official documentation, but my personal opinion agrees more or less with the hierarchy here. I do think, since we've just discovered the Higgs boson in 2012, now we have the opportunity to do Higgs boson precision physics, and that's the best way to do that is at the future E+, E- machine. But one cannot just collide electrons and protons and produce a Higgs boson. We know the mass of the Higgs boson is 125 GeV. Why not take 62 GeV E+, E- and collide those? The reason is that the Higgs boson couples to the electrons very weakly. That's because the Higgs boson coupling to the electron and to every particle is proportional to its mass. And because the electron is light, the rate of Higgs bosons produced directly in E+, E- colliders is very limited. It's very low. We cannot do precision physics with E+, E- because the rate is too low. The way to produce Higgs bosons at the E+, E- collider is by Higgs Strahlung, and that's an English word. E+, E- produces a C boson, and the C boson then radiates off a Higgs boson. This is a process that starts with, if you look at the cross-section plot at the bottom right, it starts at 240 GeV. You need to produce at least the mass of the C boson and the Higgs boson, and then you have to have a little bit energy left to push you over the threshold. Then you get a high rate of Higgs boson events. So 240 GeV, so the minimum energy that's required to produce Higgs bosons in E plus, E minus. It's crucial to have a high number of Higgs bosons to study very precisely their decay pattern, because we know very little about, we have very little knowledge about, for example, the Higgs potential in the standard model. This is something that if you go to a theory lecture, you are presented the standard model. In the standard model, you're presented with the Higgs potential, and it's just written down. Nobody knows where it is coming from, and it has not been measured either. We only know that it has a minimum that forms a Higgs oscillation, and that this oscillation is 125 GeV of mass. That's what we know. We know nothing more. And it's a very crucial property of the standard model, and it's not constrained by symmetry principles. And then there are other questions in electroweak physics, precision tests of the standard model, strong interactions, precision tests of the strong interactions, hot and dense media, by that I mean heavy ion collision, for example. The flavor puzzles that we have faced in the study of light and heavy mesons, and then to search for physics beyond the standard model. Dark matter searches and anomalous interactions. So all these should be done in the future, but we have to remember the limitations of this. Circular E plus E minus collider are limited by synchrotron radiation. And this is not a problem for linear E plus E minus colliders or circular hadron colliders. By hadrons, we mostly mean proton, proton-proton. Sometimes we also mean proton-antiproton, but mostly proton-proton. Proton-proton colliders are limited by the strength of the magnets. Linear E plus E minus colliders, they are not limited by synchrotron radiation. They're also not limited by the magnet strengths. They are limited by the achievable integrated luminosity, because a linear collider plus E minus, after the collision, that's the point of it, the bunch is lost, so you have to prepare another bunch. Therefore, you do not have a continuous data taking as continuous data taking with circular beams as the LHC or super KKB. So for linear E plus E minus colliders, we are limited by integrated luminosity. Concretely, what are the future circular collider projects on the table? You might have heard of these in the news or in the CERN Korea or in other particle physics outlets. One is the FCC, the Future Circular Collider, will be hosted at CERN. It has a diameter of 100 kilometers, and we assume that we can build magnets with up to 16 Tesla. So those would be based on neop tin instead of neop titanium. Currently, we have neop titanium. With neop tin, those magnets have not been built, but we hope to go to 16.3 Tesla. That's twice as strong as the LHC. With a 100-kilometer tunnel, we have 3.6 times the radius of the LHC. This together gives you a factor of the energy of 7.2. And this factor of 7.2, I don't want to jump back in the slides now, but you can compute this you can compute this number from our discussion of the achievable momentum at the circular collider for a given magnetic field. So this factor of 2 from the magnets and the 3.6 from the radius give us a factor of 7.2 times what we had at the LHC, which is 14 TeV, what we have at the LHC. So roughly 100 tera electron volts, which is a huge jump in proton-proton operations in terms of energy. So we would go from, well, a factor 7.2 in square root s of the beams. In terms of physics reach, this is a huge jump. There's a plan, tentative plan for a competing project in China, CEPC or SPPC, which is also a 100-kilometer tunnel with 12 Tesla or later 24 Tesla, if it can be achieved, magnets for E plus, E minus, and PP operation, respectively. This is let's say the studies towards the collider are a little bit less advanced than for FCC. For FCC, we pretty much know what the operational parameters have to be, how they can be achieved, and what the physics reach would be. And then there are future linear colliders for E plus, E minus. A famous one, an important and interesting one, is the Click Collider. It's also at CERN, with a length of up to 50 kilometers. Linear colliders are sold on the premise that they are a little bit cheaper than the expensive hadron machines. But a 50-kilometer linear collider is only a small factor, only a factor 2 cheaper than the directly competing circular colliders. The 50 kilometers is the longest extension that collider would be built. The good thing about the linear collider is that you can stage it. You cannot stage a circular collider because you cannot dig a new tunnel every few years. But what you can do is you build a linear collider and then extend it and dig it longer. That's possible until you hit a mountain. The center of mass energy for E plus, E minus would be 190 GeV, which is not enough to produce Higgs bosons. So that's too little. Up to 3 TeV. Up to 3 TeV in E plus, E minus center of mass energy. Click has an interesting two-beam scheme. It extracts the energy from a high-intensity, low-energy beam with a principle that's similar to what we have discussed when we discussed the klystrons. So to achieve a very high gradient, a second high-intensity, low-energy beam is used. I do not want to go into these details because it's a hypothetical facility. We do not know whether it would be built. In fact, we do not know if any of these projects will be built in the future. A second linear collider being proposed is the International Linear Collider operating at 250 GeV to 1 TeV in Japan. This collider project has been around the longest. It's a fully defined project with many studies of the physics reach. It's just pending the decision by the Japanese government, and that puts also the European strategy a little bit on hold, because it's difficult to decide on a future project in Europe, not knowing if there will be a competing project or a complementary project, because you want to make these things complementary in Japan. Hopefully the decision is due next year. We will see. Corona did not help And in fact, the deferring the Olympic Games in Japan also did not help, because everybody there is busy with organizing that. These are at least the rumors. Let's be a little bit more concrete. The current status for the European strategy is a result of 15 years or so of discussion, and it has been put out in June. You can follow the link here to read a little bit more about it. It's only 6 pages, and I only want to give you the high priority. One of the high priorities for the near term is to exploit the full physics potential of the high luminosity LHC. So LHC will stay on the top of the priority for at least another 15 years. The strategy is to start the R&D for the 100 TeV magnets now, and crucially, I put it in red here, to, wait, where's the mouse here? To investigate the technical and financial feasibility of a 100 TeV collider. So our current strategy is, in principle, to ask the French and the Swiss government whether they build a 100 TeV tunnel, and when they do, then we can put our magnets in and have our future collider. If they don't, it's very unlikely that that we will build a new collider in a larger tunnel, because the civil engineering is would exceed the CERN budget by an unacceptable amount. They have done it for the LHC, so we will see what happens in the future. I put here a famous slide that's shown everywhere, where the strategy is discussed, where you can see about we get an idea about the timescale. So here we have the first line is Japan, ILC, pending decision, as I've said, hopefully coming very soon. Since it's developed, tunnel need to be dug, and then ILC operation can start. It's a linear collider, so you see that the energy can be gradually increased by adding by extending that linear tunnel. CEPC and SPPC in China is here, and the CERN projects are the future circular collider in electron operation and in hadron operation. This FCCEE and the FCCHH are a tandem that's similar to LEP and the LHC. So first we do E plus E minus precision physics, and then we use the same tunnel for very high energy discovery physics. But a word of caution, look at the time scale. The time scale here goes up to 2080. This is really bizarre. I will long be dust, and you will all be old women and men once we reach this regime. So it is a very long planning to make. And these different lines here are for the different options. So currently the CERN Council prefers in the case that funding can be obtained for the tunnel, the FCCEE and then FCCHH construction. Good. This was it. I skip the wake field acceleration. It's from the last lecture, maybe less important now. And we conclude now the discussion of the collider physics. I will stop the recording for a moment. Let's switch to German.